Okay, what I want to show with the discussions on time dilation and length contraction is the physicalness of the measurement. But just keep in mind that all of these measurements can be done simply, I don't know about simply, in quotes, using a Lorentz transformation, as long as you identify the variables correctly in the Lorentz transformation. Lorentz transformation works for any problem. But I'm just trying to show the physicalness and what these things mean. Okay, so let's say we're trying to measure the length of something. How do you measure length? Now that is not a trivial question, how you measure length. It really isn't. You say, I measure length with a meter stick. Well, what does it mean? Like, how do I physically measure the length with a meter stick? What I need to do is I need to put down a coordinate system, right? So I have to put it in some coordinate system. So let's say I'm measuring the length of a meter stick. And I have to look at either end, right? So there's still two events going on here, right? So I have to look at this end and say, oh, okay, so this end of the meter stick is at the coordinate, let's say x equals 0. And then I have to walk over, right? So let's pretend I'm tiny and the meter stick is large, even though the meter stick is a meter. I got to walk over here, and then I got to look at this end. This is my eye, by the way. I'm going to look at this end and say, oh, okay, this end is at x equals 1 meter. So I had the first one where x equals 0 meters and the second one where x equals 1 meter. So delta x is equal to, I conclude it's 1 meter. I can do that because the reference frame, the meter stick is not moving relative to the reference frame. So I can take all the time in the world to look at the left end and see where it is in the reference frame, and to look at the right end and see where it is in the reference frame. So the meter stick is in the unmoving reference frame, or is in its own reference frame. If the meter stick carries coordinate axes with itself, we can measure the distance between one end and the other end. So again, the events really are me looking at one end and me looking at the other end. And as long as it's stuck to its coordinate frame, then we can just mark on the coordinate frame and say, oh, look, that's at 0, and that's at 1, and there's 1 meter between them. Now, what's interesting is think about, and you might say, but aren't I a moving reference frame? Aren't I a moving frame? Well, I'm stationary to the frame at the left end, I move over to the right, and then I'm stop, and I'm stationary relative to the frame at the right end. But think about a reference frame that is moving by. A reference frame that is moving by at speed v. What distance are they going to measure? They cannot stop at the left end and C and the right end and C. They're moving by. They may be all the way over here, right? And so they may be, way beyond the meter stick by the time they can pin down the left end and the right end. So how do you move something how do you measure the length of something that's moving relative to you? It's easy to measure something that's stationary relative to you because you can just put down a stationary reference frame and mark down on it. But when it's moving relative to you, you typically measure the distance by measuring how long it takes to go by you. So delta x prime is going to equal to the velocity of the meter stick times how long it takes the meter stick to go by me. Okay, again, so I could be flying by this meter stick. At t equals 0, I'm at its left end. According to my frame of reference, at t prime, t prime equals 0, I'm at the left end. At t prime equals, 1 second, I'm at the right end. So I now know the length of the meter stick was equal to my velocity times however long it took me to traverse the length of the meter stick. So really, it's the length of the meter stick, according to my frame of reference, is equal to my speed versus times how long it took me to traverse the length of the meter stick. So in the meter stick's frame of reference, we'll call L equal to 1 meter. That's the length of the meter. In a moving frame of reference, moving relative to the meter stick, we're going to get what's written down at the bottom. Who measures the proper time? If Mary's in the moving frame and Frank is the one who's in the stationary frame, who measures the proper time? This is tricky. Or maybe it's not. Who has a watch that is in an inertial frame that is at both events? And that is actually Mary, right? Mary's in an inertial frame. And so she's got a watch, right? This is supposed to be actually a watch face. I don't know. She's got a watch. And that watch is at event 1, measuring the left end. And it's eventually at event 2, measuring the right end. right? So Mary's got a watch that's at those two events, and this is Mary's equation. Frank does not have a watch at both events that remained in an inertial frame, right? So if we put a watch here and we say at t equals 0, we measure the left end, that watch is not at the right end. And in order for Frank to get to the right end, I said Frank had to get out of the inertial frame but then got back in the inertial frame. That doesn't count in terms of proper time. He is no longer measuring a proper time. The person who measures the proper time is the person who is moving in an inertial frame who has a watch present at both events. And maybe we didn't say inertial frame before, but that wasn't certainly meant to be implied. Okay, so now if you believe what we're saying, and you should, then this is the proper time. But how far would I say Mary has moved? Mary says that the meter stick has moved L prime relative to her. So Frank says that Mary has moved from one end of the meter stick to the other end of the meter stick, right? That's what Frank says, that she's moved from one end of the meter stick to the other end of the meter stick, and she's moved at V in a time delta t. And Frank is the one who says the meter stick is 1 meter long. So who has the proper time? Mary. So this is t0, and which is equal to delta t over gamma, right? Because all other times are longer. T0 is the shortest possible time, so all the other times are longer. So that's delta t over gamma. And I can then go ahead and combine these two equations to show that L prime, which is V delta t over gamma, must be also equal to V delta t is L over gamma. So L prime is L over gamma. So what you want to realize here is that Mary, who's moving relative to the meter stick, she's measuring L prime. Frank, who is stationary relative to the meter stick, he is measuring L. Mary measures something shorter than Frank because gamma is greater than 1. So we write this as L prime equals L0 over gamma, just like we write delta t prime is equal to gamma times t0. T0 is the shortest time, and L0 is the longest distance, right? That all moving frames, remember L0 is the distance measured in the stationary frame relative to the object. All frames of reference moving relative to something measure as shorter. So moving meter sticks shrink. Everything that moves relative to you appears shorter than it is. And not only appears, but is shorter. That the meter stick is shorter relative to you if it's moving relative to you. How much shorter? Right? In the frame of, in the scheme of things, when we're talking about velocities that are much, much slower than the speed of light, it's not that much shorter. It may be immeasurably shorter, but it's shorter.